Thanks a lot. So it's a pleasure to be here. I was here in 2009. It was a lot of fun, so I hope you guys are having a lot of fun too. And I'm going to be talking about dark matter, so continuing kind of the discussion you've had already. And let me give an outline of what I'll talk about. So today, I'll just focus on the landscape of dark matter models and what we know about dark matter. So I'm not at all going to give you an overview of every single model and their, all the top-down motivations, things like supersymmetry and so on. I'm not going to talk about that. Instead, I'll just focus on the landscape of models in relation to the observational evidence we have, and just very broadly, what can we say in the most generic terms. And then the next two lectures will be starting to focus on models of thermal relic dark matter and moving into specifically light dark matter that I was asked to talk about. So meaning, see this again, thermal relics and sub-GeV dark matter. So I'll motivate why that's an interesting mass range to look at and what the models are there and the kind of cosmology of sub-GeV dark matter. And then the last two lectures will be, if all goes according to plan, the last two lectures will be related to direct detection. So the first lecture I'll give on this will review the formalism and intuition for direct detection of WIMPs, or nuclear recoils. So this is what's usually being searched for in ton-scale experiments. And in the very last lecture, I'll get to new directions for detecting the sub-GeV dark matter, which is hard to probe with ton-scale experiments. And this is the topic I've been working on for the last few years. So hopefully you'll get to see some pretty new stuff by the last lecture. Okay, so as I said, today I'll just focus on general things we can say about dark matter. And I don't want to give a history of all the evidence of dark matter. We know there's lots of different pieces. You've probably talked about things like rotation curves and so on. So today I'll start with kind of what is one definition of dark matter we can make, and then use that to guide what we can say about the cosmology of dark matter, and eventually to guide the model building. Okay, so for the first part of this lecture, I'm just going to talk about dark matter in cosmology terms, meaning it's a cold fluid. So it's a fluid with density perturbations. It has velocity perturbations. It has an equation of state where this is 0. And this basically defines what you need to know to start to calculate things in lambda CDM. Okay, and this reproduces very well things like large-scale structure and the CMB and so on, and it's how we obtain our measurements of the average amount of dark matter there is today in the universe. And this is a working phenomenological approach that it works extremely well. It says nothing, of course, about the particle physics of dark matter. It's just a description, an effective description in terms of these density, in terms of this fluid. But of course, what we really want to get at is what is the underlying particle physics. And many different models can reproduce this. We don't need to specify what it is in order to fit the data well. Okay, so one of the main predictions of lambda CDM is the matter-power spectrum. So I'm going to spend some time going over the matter-power spectrum in detail. And try to draw straight lines. So this is I'm going to plot here the power spectrum, the dimensional power spectrum. So when it's 1, basically the density perturbations are of order 1. And that's when perturbations can go nonlinear. And this is, again, as a function of k, which is an inverse scale, inverse length scale. This is what I'm going to sketch right now is taken from one of Mark Vogelsberger's reviews. So I'll just cite it here, and he will tell you much more about this. Oh, I forgot the last name. Okay, so the lambda CDM prediction looks something like this in very heuristic terms. On large scales, this is CMB / cosmic scales. Perturbations are still linear, and there's a transition point at around 10 to the minus 2, where into the nonlinear regime. So I'm plotting, this is the linear matter power spectrum. Around here we have things like clusters and galaxy scales or galactic scales, and Lyman alpha are down here. And then there's small scales. I'm going to draw a rough boundary around here where there's very few measurements of what the power spectrum actually looks like. Okay, so I'm not going to go over all the observational evidence, but there are measurements throughout this entire range agreeing with the predictions of lambda CDM. Okay, so I'm going to return to this in a second, but yes? Is it supposed to? Yeah. It is supposed to be close. I don't know if the plot is it's a very heuristic plot. Yeah, it's around there, yeah. Okay, so what we learned from this, well, one thing we can learn is what our cosmology looks like as we look back in time. If we look at smaller and smaller scales, those correspond to dark matter density perturbations that started evolving further back in time. Okay, so they tell us something about the behavior back to redshifts of 10 to the 6, I'll show. So what now I'm going to plot is for a given length scale, we have a density perturbation. At what redshift did that length scale start evolving in the cosmology? So the way I'm going to do that is if I take a given k mode, that corresponds to a length scale of 1 over k. And if I go back in time, I have to account for the fact that we have an expanding universe, so I need to include the fact that I need to include this scale factor at an earlier time. And at some point when this, at some point this, the size of this perturbation will be equal to the horizon size. So remember that Hubble is an expansion rate, and so 1 over Hubble gives a time scale or horizon size. So the condition for when this k mode started evolving is that k equals AH. So I'm going to plot as a function of redshift what this quantity, this Hubble times scale factor is. And that will tell us when a given mode came into equilibrium or could start evolving. Again, very heuristically, this is AH. Z equals 0 is today. Z of 1,000 or so is when we say CMB. Matter radiation equality is around Z of 3,000. And then on my log scale, this will be about 10 to the 6. Okay, so let's look at this very small scale where things start to become unknown. So in this plot, 10 is going to be around here, and this is 10 to the minus 2, let's say. So this peak is around where matter radiation equality is, and this is about 10 to the minus 4 or something down here. So this very small scale, k greater than 10 or so, will cross this line at redshifts of around 10 to the 6, somewhere around there. I know I didn't intersect them properly, but it'll be around redshifts of 10 to the 6. So in the standard cosmology, what we have is, if we have a density perturbation of size 1 over k, it's frozen when it's outside of the horizon, or when it's larger than the horizon size. But once it becomes smaller than the horizon size, it can start evolving. At that point, it's sensitive to what kinds of dark matter interactions are present, or whether dark matter is really behaving as a cold fluid or not. Okay. So let me draw this as kind of the unknown region. We can kind of play with different dark matter models that affect the physics up here at high redshift, and it will only affect small scale structure. And this is something is not a fixed boundary, of course. There are a lot of people working on better understanding small scale structure. It's an active area of research. So let's see what this tells us about dark matter. One is, let me plot on the top axis, which hopefully you can see. As we look back in time, the photon temperature is increasing, right? So it redshifts as the universe expands. And as we look back in time, the photon temperature is going to be whatever it is today, but counting for the redshift. And today is. So today, it's the CMB temperature, is 2.7 Kelvin, which is going to be a few times 10 to the minus 4 eV. Oh, this is a gamma and gamma 0 for today. Yeah. And so that's the temperature today, around 10 to the minus 4. If we look back in time at around CMB, or matter radiation equality, it's going to be around EV because of this factor of 1,000. And at around 10 to the 6, redshifts of 10 to the 6, it's going to be around keV. So this immediately tells us something about thermal dark matter, and gives us this warm dark matter bound that many of you might have heard of. The idea is, so we want to use these two results here to start making some statements about the behavior of dark matter. And so one of the statements that's often made is that it has to be cold, it cannot be warm. And this is often quoted as a warm dark matter bound greater than keV. And our discussion here already tells us why that has to be the case. So let's take a dark matter candidate which has a mass of around keV, or a little bit lighter than a keV. Then it was still non-relativistic, or sorry, it was still relativistic at around this time. But this is also a time when density perturbations have to start growing because we start to observe the matter power spectrum. But if we have a non-relativistic candidate, there's a huge pressure, and that doesn't allow the perturbations to grow as fast. Yes?
Sorry, so this is before matter radiation. Are your perturbations growing at this time, or are they just oscillating and then something else funny happening?
They grow slowly. So they don't grow as fast because it's radiation dominated, but they do grow logarithmically. Yes?
That bound is like thermal.
Yes, exactly. So you have to assume that the dark matter temperature is similar to the photon temperature. Or whenever people quote those bounds, they make a specific assumption about what the temperature is.
How relativistic is relativistic? People often treat this as a binary. There's a continuum.
Exactly, yeah. So the question was how relativistic is it? And really the best way to answer it is like take your model and take what the temperature is and see how you change this matter power spectrum on the scales where it's measured. So we have, this would be something like a warm dark matter candidate. And really you have to compare where this cutoff is. There's a cutoff because, again, perturbations cannot get damped out when the dark matter is relativistic. And you have to compare the cutoff to the strongest bounds are from Lyman alpha observations. Okay. So this cold dark matter statement can be turned directly into when could there be a exponential cutoff in the matter power spectrum. This is for thermal dark matter. Okay, so, and specifically, we can state it as it's non-relativistic by redshift of around 10 to the 6th. The next thing that we can learn from this is the collisionless property of dark matter. And again, there are different ways in which you can say dark matter is collisionless, but again, focusing on this picture we have here. If there were particle interactions, so let's look at some redshift just below 10 to the 6th. If there were particle interactions that were present between the dark matter and the standard model, that would again lead to a pressure that prevents the dark matter from growing, or the dark matter perturbation from growing. Right? If it's coupled to the standard model, that will be a radiation pressure, and it will lead to acoustic oscillations like this in the dark matter, similar to the way that there's acoustic oscillations in the CMB due to the baryon photon fluid. So this would be something like called collisional damping. If there are collisions, there will be a damping in the matter power spectrum. And so you have to make sure that whatever interactions you have, they turn off by a redshift of about 10 to the 6 again. And of course, this also means this collisionless property can also mean other things if you're looking within galaxies and so on, but at least this is the perspective for the early universe. There are dark sector models where the dark matter couples to its own radiation bath, so it's a dark radiation bath, and that that has a slightly different name. It's usually called dark acoustic oscillations, but it would also lead to a similar effect. So, and dark matter, dark matter. Okay. Another property, of course, is that dark matter has to be stable on the age of the universe. So I won't sketch it, but this is, again, something you can constrain with the matter power spectrum. So there have been papers looking at, suppose you have dark matter and it decays, you can decay into something relativistic. So that's sort of like a little bit of the matter density is leaking into the radiation density. And that, again, affects this matter power spectrum. And you can constrain it even though you're not directly observing the decay products. Yes?
I have a question. So on the recurve, why would the light from the existing dark matter just sharp turn down the small scale structure in the presence of photons? Presumably they're doing the same thing, that they are just relativistic species that have to raise the structure. Why is that like a drastic effect?
So you want to know about why it's such a sharp cutoff? Yeah, so the photon perturbations can't grow, and also when the dark matter is relativistic, it can't grow. And so all these modes came into equilibrium, became smaller than the horizon size much earlier on, and instead of growing, they get damped due to their essentially free streaming because it's radiation. I'm not sure I totally understood the. Okay, yeah.
I think that depends on how interactions scale with time.
Yeah. Yes.
How do the dark matter interaction balance that you get from this collisionless condition, how do those compare to like bullet clusters?
So, right, so the question is, how do these dark acoustic oscillation bounds compare with the bullet cluster? And the answer depends a lot on the scaling of the, well, one is that the dark acoustic oscillations, there has to be a radiation bath, like a dark radiation bath that you're scattering against. And for the bullet cluster, they're usually quoted as dark matter scattering. So it's not always directly translatable. And the other thing is that in the bullet cluster case, or the scaling of the interaction between CMB and bullet cluster is model dependent. So it also depends a little bit on the model you have. So for instance, if you have a very light mediator, which for the dark matter self-scattering, then you can have a very big effect on the bullet cluster, whereas otherwise you might suppress the bullet cluster effect and have a bigger effect in the CMB. Okay. Okay, so gotten to our stable condition. Again, you can say, you can look at, for instance, you can look at how much, what fraction of the dark matter could decay on the age of the universe, and the answer, as you might expect, is very small, much less, about 1% or less. And if it decays to visible products, you can say a lot more, and probably Dan Hooper will talk about that. Okay, so these are kind of the main properties of dark matter that we can infer from looking at the matter power spectrum and this evolution of the modes. And the last one is, that I'll write down, is preserves BBN, because this will be important for the kind of model building that I'll be talking about. Of course, this looks back way further in time, but we just need to make sure that we reproduce the successes of BBN and don't introduce too much extra energy density that could change what the relative abundances are. Okay, but it doesn't necessarily mean that we had cold dark matter at this time. It could have been somewhat relativistic. We don't know. Okay, so move to the last board. Yes.
So for the long dark matter regeneration case, for that case, dark matter has that kind of better power spectrum and the matter is smaller. And from there we get the bound.
Yes, exactly. If you have the warm dark matter case, then you can use the Lyman alpha measurements as a direct probe of this matter power spectrum.
So the bound is from the very short window below the thick line. You mentioned not the thick line,
Yeah, exactly. So for instance, the Lyman alpha constraints will quote what they will look for is whether there's a cutoff in the matter power spectrum. And so different groups obtain different things depending on the modeling you do and what data you look at. So that's why it's a very thick line. But they don't see a cutoff in the matter power spectrum. And then you could push it, and it's very hard to see, say, like 10% changes in the matter power spectrum. So you could push a cutoff in the matter power spectrum to just smaller scales than observed. Okay, so given these properties that a dark matter candidate has to satisfy, I'm going to go over the dark matter mass, the possible dark matter mass range, and very briefly allude to the models in this mass range. So, not to scale, of course. So we're going to have a boundary here. This is a bad place to put the boundary. We're going to have a boundary here, KeV. And again, that KeV is my warm dark matter bound, roughly. So if I have thermal candidates, they're going to be above mass of around KeV. And we'll get to the derivation of the upper bound that people often quote on this thermal range of about 100 TeV. So by thermal, I mean that the dark matter was in thermal equilibrium with a standard model at some point. Here we have our WIMPs. And here's the sub-GeV window that I'll be talking about later on. So there's another bound at about a keV, so definitely thermals up here. And there's another bound at the keV mass range, which I want to discuss a little bit. And that's often called the Tremaine gun bound, but there are various. The thing I'll present is not exactly the Tremaine gun bound. I'll explain why. And the idea is that this KeV mass scale also is a boundary between when dark matter can be a fermion versus a scalar. So, or boson versus fermion, let's say, not scalar. Okay. So this bound relates to how much dark matter you can fit in a given volume of phase space. So this is my phase space density of dark matter, and if it's a fermion, then it has an upper bound because of polyblocking, fermion statistics. So G is just whatever degrees of freedom. I could have spin or some flavor or something else. And in my units where h bar equals 1, this is the bound that I would have, the most generic bound I would have on what the phase space density of dark matter could be. This x is the dark matter. So just remove that because I'm only talking about the dark matter phase space density, and this is position and momentum. Okay, so I can look at just locally how much dark matter there is. So these are useful numbers for any dark matter physicist to remember. I want to look at n dark matter. So n dark matter locally, we can write as the number density of dark matter over the mass. And it's useful to remember that this is about 0.4 GeV per centimeter cubed. It's also somewhat useful to remember this number in electron volt to the fourth, but I have to look at my notes to remember, so 3 times 10 to the minus 6. So this is the number density that is essentially measured up to, say, order 1 factors. We know this probably to within 50% or so. And this is, now we can calculate the maximum number density we can have given this phase space bound. So to do that, I integrate over all the possible momentum states. And I want to integrate up to a maximum momentum. That maximum momentum is going to be set by the escape velocity, again, locally in the solar neighborhood. So, again, a useful number to remember, it's about 500 or 600 kilometers per second, or 2 times 10 to the minus 3 in units of C. Okay, so this integral is just, of course, G P max cubed, and I'm just going to drop the factors of pi for now. So now if I relate the number density here, so it's going to be to the one that's observed. Well, so it's a bound, so we want this to be, should be greater than. Exactly, yeah. So this is a measured number density, and this is an upper bound on the phase space density. So the number density has to be less than this quantity, So if this quantity is less than the observed value, then we have no hope of getting the observed number density, right? If the maximum number density is less than this, we have no hope. So we have to say that at least the maximum allowed phase space density integrated should give at least this quantity, because this is a very conservative estimate of what the phase space density is. Yes? Oh, sorry, there was 2 questions. I forget.
Okay. Vary, so I can imagine a scenario where higher ones will have more degrees of freedom. Or that's going to be a constant no matter what the scale we talked about.
Yeah, this is for a given candidate, this is a fixed number, but certainly once you put in like a realistic velocity distribution, then things can change. Yes? The escape velocity is around 500 or 600 kilometers per second. That's something you can measure by looking at the stellar distributions and looking at where the stellar distributions cut off, because they would also have a similar escape velocity. Yeah.
Shouldn't there be an F?
And F. Oh, yeah.
Oh.
Sorry, I skipped a step. Yeah. This is an F, and I replaced it with G. Yeah. Yes? This up here. So this is the bound I'm deriving right now, which I'll get to in a second, which is that if I have a fermion, the mass cannot be below around keV or 0.1 keV, a fermionic dark matter candidate. And so I restrict all candidates below that mass range to be a boson. Okay. So let me finish getting exactly what the bound is using the local density in the Milky Way. This is about 10 to the minus 9. So I get that mx to the 4th is greater than about 10 to the 4 or 10 to the 3 electron volt to the 4th. Let's put the G back if you want. And so that implies mx is greater than about 10 eV. That's not exactly the keV bound I said, but that's because I was looking at an example of the Milky Way, the solar neighborhood where we are in the Milky Way. Now you can repeat this kind of exercise for different kinds of systems. If you look at like dwarf galaxies and so on, then you'll get a stronger bound. And that's about 100 eV. Yes?
So I'm a little confused about the direction of your inequality. So if like if your the integral number density has to be less than this thing, then why is it that the result of that integral has to be greater than the integral? I'm confused why that's correct.
Yeah, let me repeat this. Good. So this is the maximum possible density in the very conservative case where I have maximum phase space density. If this quantity is less than the observed number density, then I'm out of hope. There's no way I can get the observed number density.
Okay.
So if this quantity is greater than it, then I have some hope, even though it's a kind of, I may have to pack everything in maximally, I have some hope of getting it to work out. So this is true for fermion. Yes? These two? So, okay, so I can refer you to a paper that does it for a bunch of different dwarf galaxies, and this will be, depending on the assumptions you make, this can vary within 100. So it could be 100, it could be 200, 300, 50, yeah. And actually the original Tremaine gun bound is even stronger. It goes up to keV. And that's because they make an even stronger assumption that the dark matter was in thermal equilibrium at some point. And so that changes, that changes the argument a little bit, because they can use the fact that the phase space densities get conserved to place a stronger bound. But in any case, the mass scale is around 0.1 keV or keV, where we can no longer allow fermionic dark matter candidates, just from the observed dark matter halo. Okay, so everything down here is a light bosonic dark matter. We have somewhere around here, let's say, QCD axion dark matter. But we also have generalizations of that, axion-like particles and so on, that can go down to this mass. Yes? I'm just being heuristic here, because in most cases, unless you put in like 100 flavors or 1,000 flavors, it'll be an order 1 number. So I just assume, say it's a spin half particle, maybe G is 2, and it's not going to change the number too much. Yeah, but definitely you could do something and just weird and just make G a huge number. Okay, so everywhere here is a scalar down to, boson down to 10 to the minus 22 eV. This is fuzzy dark matter. I forgot to mention one other thing around this degeneracy pressure for fermions. Some people have used it to try to get more chord profiles in dwarf galaxies. Again, using the packing, this packing argument, then it's harder to get cusps as you go into as you go to the centers of certain dark matter halos. And people have tried to use that to explain the profiles where some of them were more chord than expected. So let's also see briefly the arguments for why we cut off this lower mass range at about 10 to the minus 22 eV. And so one of the original papers that's usually quoted is by Kana and Grozanov. The idea here is that we can also look locally in the solar neighborhood, and we can look at the de Broglie wavelength of this dark matter candidate. So I told you the escape velocity is about a few times 10 to the minus 3. The typical velocities, not the escape velocities, are also about 10 to the minus 3. And so I can translate this into astronomy scales. So it turns into 4 kiloparsecs for this mass. So that's not necessarily deadly in terms of what we know about dark matter structure in the Milky Way. We don't know things down to the kiloparsec level. So as reference, the size of the Milky Way disk is probably around 20 kiloparsecs, the observable disk. 10 to 15 parsecs. But if you look in dwarf galaxies, the velocity dispersion is even lower. It's about 10 to the minus 4 instead. and this gets turned into, say, order 10 or 40 parsecs, depending on the dwarf galaxy you're looking at, and that becomes comparable to the size of the halo in a dwarf galaxy. And so that starts to set limits on what the lightest mass can be. If it's lower than this, then you cannot form the observed halo profiles in dwarf galaxies. Yes?
How do we know a typical dark matter particle velocity? Like, how is that in any way observable?
So I mentioned that the escape velocity comes from looking at the velocity distributions of stars. And so this can come from a similar way. Stars are essentially collisionless, and we also have what's known as a stellar halo. So you have this picture of the disk. We have the dark matter halo kind of all around it, and everything in the dark matter halo kind of moves isotropically. We also have in here what's called the stellar halo. There's lots of stars, they're not in the disk, but they also just move kind of isotropically with a spherical distribution. And we can look at that, for instance, to infer something about what the velocity distribution of dark matter has to be, because they're both determined by the gravitational interactions.
So wouldn't something with a mass of -22 eV that's going close to 500, 600 kilometers per second, that sounds like that ought to be fairly relativistic, that mass velocity.
So it's still non-relativistic because v is still 10 minus 3.
Okay.
Yeah. Okay, so v is about 10 to the minus 4 in dwarf galaxies. And if you look in the early universe, you can have even smaller velocities. So these velocities are set by the halo dynamics. But if you look in the early universe, where you didn't really have such high dark matter densities, then these velocities are even smaller. And another strong constraint giving this lower mass bound is, again, this matter power spectrum. In the early universe, because the velocities are so small, this de Broglie wavelength is large, and again, you prevent collapse of structures on small scales, and you get a cutoff. You can get a cutoff in the matter power spectrum. So one bound is from dwarfs, and another bound is from, again, Lyman alpha. So these candidates, they don't have to have any particular coupling to the standard model. They could be formed by misalignment. So in most contexts, we can treat them as a classical field. So if we look at the occupation number of this dark matter, it's given by, again, the number density. Now I'm going to multiply by volume given by the de Broglie wavelength. And this occupation number, you can go ahead and plug in the numbers as before, and plug in this dark matter density as I gave you earlier. And it'll be about 100 for 10 EV scalar. And you can imagine, sorry. Did I get the power right? Yeah, this is not a 2, that's right, I was confused. Okay, good. So it'll go as 1 over mass to the 4th. And already for around 10 EV or so, you're getting pretty large occupation numbers. Certainly as you go down to 10 to the minus 22, this is going to be huge. So we often treat it as a classical field. So I'm going to write field-like. So it's field-like down here, and kind of particle. We usually describe it as particle-like up there, though Again, these are not strict boundaries.
So I'm wondering about velocities. If you, let's say you produce a really light particle essentially at rest, would you naturally get to those velocities just from gravitational collapse? Or do you have to, hand pick the sort of like the right initial velocity distribution?
Yeah, the assumption, so you can ask like what sets all of these velocities, and yeah, the assumption is that everything is produced with almost zero velocity, and as you get density perturbations that are growing, this will lead to velocities set by the gravitational potential, and that's where all of this will come from. And so that's why you can estimate in the early universe the velocities are even smaller. Okay, so these dark matter candidates, they behave like a scalar field. So it's useful to look at how they behave and convince ourselves that they behave like cold dark matter. And so if we have a scalar field with mass m, they obey the classical wave equation. But when there's when there's a Hubble expansion, then we have to add in a Hubble friction term. Okay, and there could be, if you put in an arbitrary potential for the scalar field, there could be some other things here. But I'm just going to assume that it's just the mass, the m squared phi squared term, that's just a free scalar. So when the Hubble expansion rate is much greater than the mass early on, phi is approximately constant. And the solution, once the Hubble rate drops below the mass, looks like there's an oscillating piece, oscillating with the mass, and there's this envelope here, which I'm calling C of t. So it's a useful exercise to go through this and see what the solution for C of t is, but I'll just tell you what it is. It's given by, it can be written as 1 over a of t, scale factor to the 3/2. This is an approximate solution. You can find the exact solution. But what this tells us is that if we look at the energy density, oops, so it's given by the potential term plus the kinetic term. We're ignoring spatial dependence. So this A of t is changing at a much slower rate than this sine mt. So in this derivative, I can just take the derivative of the sine mt, and I'll get approximately, so this will just give oops, 3. So this tells us that the energy density in this field is decreasing as the scale factor cubed, which is what we expect for cold dark matter. We need this to start happening by matter radiation equality. Otherwise, we don't have any matter to get to matter radiation equality. So that condition tells us that H at matter radiation equality we can set that equal to m. So this expansion rate can be written as t squared over m Planck times g. So this is only true, we'll go over lots more related to this in the next lecture, but this is only true in the radiation-dominated era, but since I'm just at matter-radiation equality, I can still approximately use it. And the temperature at matter-radiation equality, remember, is about an electron volt. So this is about eV squared over the Planck mass, which is 10 to the 19 GeV. So I put another 10 to the 9 here to get to EV. So this tells us that the Hubble rate matter radiation equality is about 10 to the minus 28 EV. So since our lower limit is 10 to the minus 22 EV, we're safe. That means that for this mass, this scalar field was behaving like a cold dark matter candidate well before matter radiation equality, so all is fine. Yes?
Quite understand that. So why were we setting h equals n? Because, well, that was the difference between phi being constant and phi being oscillatory.
Right.
Why were we also associating that with matter radiation equality?
So this solution tells us that the scalar field only behaves like cold dark matter after this condition. So once the Hubble rate drops below the mass. So the transition point for when it behaves like cold dark matter is when we set these two equal. And the very, very latest I can imagine that happening is when I need matter radiation equality to happen by. But of course, it's much stronger than that, as we saw, because of the fact that we measure the matter power spectrum even beyond matter radiation equality. Interestingly, this is not exactly W equals 0, so it does not exactly have the equation of state that you would expect for cold dark matter. It actually, because of this sign of MT, it actually oscillates between -1 and 1, but it averages out to 0 on any time scale larger than 1 over m. So so to summarize, this solution looks something like this. Something sets an initial condition here, and when we reach this condition that the Hubble rate is equal to the mass, then it starts oscillating about 0, but with the total energy density approximately constant up to this scale factor.
So actually, just going a couple steps back, so the comment about we could actually pull it all the way to maybe like KV or something like this from Lyman alpha. So does that basically gives it 10 to the minus 22?
Exactly, yeah. So the 10 to the minus 22 comes from the Lyman alpha. So this was very conservative, that we needed to behave like cold dark matter at matter radiation equality, but really we see from this picture that it needs to behave like cold dark matter by this KeV temperature, or 10 to the minus 10 to the 6, and that gives you the stronger bound of 10 to the minus 22 EV. Okay, so since these are set by misalignment, there's not a required standard model coupling, but of course there's lots of models, or for instance the QCD Axion, where there are motivations to have the standard model coupling, and you probably heard last week or the week before about ways which we can search for those couplings. Misalignment means anything that sets this initial condition. So something sets the initial field value. So here's a potential, m squared, phi squared. Something forces the initial value to be up here. That determines, you can see from this, the energy density, that determines the amount of dark matter we have today. But it really is just a generic term for something that puts the value away from 0. And you can do it by inflation or something else. Okay, so we've covered most of this range. I'll go over again the motivation for this range, but let's look even at higher masses now. We do have particle candidates between this 100 TeV range and the Planck mass. There are things like WIMP-Zillas and just other heavy particles that have to be produced non-thermally. But at least we can imagine, a particle candidate up to the Planck mass. Beyond that, it gets more dicey. We need to, most candidates are things like composite objects. So they're not really fundamental objects of size greater than the Planck mass, but they're really composites of, they could be composites or they could be, similarly nuggets of lighter things with enormous, one has to get to put a huge number of these together, and there's a lot of questions about how you actually do that. Say you need like 10 to the 10, accumulate 10 to the 10 masses into a composite object. Okay, and this is definitely not to scale, but finally, at the very high mass end, there's one other candidate that at least we know of, the primordial black hole candidate. So these composite candidates are hard to form. They're usually formed by some sort of strong force, some sort of strong force between lighter dark matter particles. And then in the primordial black hole case, again, we're back to not considering necessarily a particle candidate at all, but density perturbations that were extremely large that collapsed in the early universe.
So with the classical field, you mentioned that the equation of state is oscillating between 1 and -1.
Mm-hmm.
So I see that averages out to 0, but when it's -1, you have this exponential contribution.
Yeah.
So it seems like the exponential part should dominate. You see what I mean?
Yeah, I see what you're saying. As far as I know, this has no observable consequences, but is there, and I don't know of any observable consequences. So one way to form primordial black holes is again to use this matter power spectrum and the fact that we don't know that much about it. And way out here somewhere, you could imagine something producing a spike in the matter power spectrum at very small scales. That spike means very high probability for any perturbations of that size to collapse. So it could be during a radiation-dominated era, but if you have a density of perturbation that is much bigger than 1, then it can still collapse into a black hole. Okay, and so since we're coming to the end, I'll just give a brief summary of the allowed mass range for primordial black holes. We have a lower mass limit of about 10 to the 15 grams. This is about 10 to the minus 18 solar masses. That comes from looking at the lifetime of the black holes due to Hawking evaporation. If they're lighter, then they evaporate too fast. There's the very upper bound of about 10 to 50 solar masses, depending on which bound you take. This is mostly coming from accretion onto these black holes, which would give rise to observable signals, or radiation from these black holes, essentially. And everywhere in between, the allowed fraction of primordial black holes, the primordial black holes can be about 10%, few to 10% of the dark matter. Except for one mass range where there may be reasons to believe that it can be a little bit bigger. So there's a particular window. Let me see what it was again. 10 to the minus 14 to 10 to the minus 11 solar masses. And in this window, there are some open questions about the constraints that are present, that are usually quoted, which imply that, well, depending on how those constraints turn out, they still need to be understood a little bit better. This could be order 1 of the dark matter. But it's not entirely easy to get these spikes in the matter-power spectrum to produce primordial black holes. You could do it during inflation, for instance, but you definitely need to kind of fine-tune your inflationary potential in order to get a region where you get a huge spike.
I'm sorry, the upper bound was coupling or
You can, these primordial black holes, these massive ones, the bounds come from looking at accretion onto these black holes and then looking for X-rays and other things. Yes?
What about the overall
This point, you're asking about what about this 10% number? So this number is coming from lots of different searches in this mass range, between 10 to the minus 18 solar masses to 10 solar masses. There are lots of different searches. For instance, lensing. They're looking for lensing events by the black hole. And so if you drop the number density of the black holes, say in our galaxy, then you can get around those limits because you just wouldn't have enough lensing events given the statistics they have. Yeah. Yeah, the lack of observation of these lensing events. Yes?
I think you said that the lower bound, 10 to the negative 8 solars, was because otherwise they would like evaporate or something.
Yeah.
So how is this other category window so far below that? Why wouldn't they have evaporated?
Oh, so, yeah, this is 10 to the minus 18. Sorry, yeah. Yeah, sorry, this is 10 to the minus 18. This is 10 to the minus 14. Okay, so I think we have a few minutes left, so I'll just wrap up. Okay, so today we just looked at the broad range of possible dark matter candidates, and I focused on these general arguments that can separate this entire dark matter candidate mass range into different regions. The motivations for focusing on this thermal window here, well, there are a couple. One of them is that everything we know was in thermal equilibrium. The relic neutrinos were in thermal equilibrium and are a thermal relic. The CMB is a thermal relic. Modulo the fact that we don't know where the baryon asymmetry comes from. We don't know why the baryon to anti-baryon number is what it is, or baryon to photon number is what it is. Modulo that, everything else we know was produced in thermal equilibrium and is a relic. So that's one reason. It kind of generalizes what we already know and know works. The other is that because it's a thermal equilibrium with a standard model, again, it implies some sort of coupling with the standard model particles that we can then go search for. And of course, that's motivated the WIMP window, lots of dark matter searches in the WIMP window. And I'll discuss how we can broaden that and look at searches in the sub-GeV window that test very similar ideas of a thermal coupling with a standard model. But these have been much less explored because, because of the focus has been on WIMPs traditionally. So in the next lecture, I'll just talk about this thermal window and motivate the considerations that lead to this sub-GeV dark matter candidates. So that's it for today. Thank you.